air gaps. Before continuing with the illustrative examples, let us consider the effects that an air gap has on a magnetic circuit. Well, over here, as you can see, that due to air gaps, the spreading of the flux lines outside the common area is known as fringing. While doing the math, we have to ignore this fringing effect. We will assume that all the flux lines will pass through the air gap and there will be no fringing. That is, we will be considering the ideal case while we solve the maths. The flux density of the air gap can be determined using the formula Bg equals phi g by Ag, where phi g will be equals to phi core and Ag will be equals to A core. The magnetizing force of the air gap is determined by using the formula Hg equals Bg by mu naught, and the MMF drop across the air gap is equal to Hg Lg. Problem 4. Find the value of I required to establish a magnetic flux phi equals 0.75 into 10 to the power minus 4 Weber in the series magnetic circuit. So, in this electromagnet, the core is made of one type of material, that is cast steel. However, there is an air gap present. The area throughout is 1.5 into 10 to the power minus 4 meters square. Assuming no fringing effect, phi equals 0.75 into 10 to the power minus 4 Webers. The lengths are given over here. N equals 200 and we have to determine I. The equivalent magnetic circuit will look like this, where F is basically the product of Ni, and there will be two reluctances, one for the core and the other one for the air gap. The flux density for each section is B equals phi by A equals 0.5 Tesla. Using the BH curve, we can determine H for cast steel, which will be equal to 280 ampere turn per meter. And applying the formula which we have seen in the previous slide, we can determine Hg to be equal to 3.98 into 10 to the power 5 ampere turn per meter. The MMF drops for the core is 28 ampere turn and the MMF drop for the air gap is 796 ampere turn. Applying Ampere's circuital law, we can easily determine I, which is equal to 4.12 ampere. Example. Determine the current I required to establish a flux of 1.5 into 10 to the power minus 4 Weber in the section of the core indicated. That is, according to this figure, the flux established by the product of Ni I, which is the magnetomotive force, is phi t. We know the value of phi 2, which is 1.5 into 10 to the power minus 4 Weber. We have to determine the value of phi 1 and phi t in order to determine the value of the current. All the other informations are given in the question. The equivalent magnetic circuit and electric circuit analogy are shown over here. We know the value of phi 2 and we know the area of cross section. Thus, we can easily determine B2, which will be equal to 0.25 Tesla. Using the BH curve, we can determine the value of this section, which is equal to 40 ampere turn per meter. Applying Ampere's circuital law around loop 2, we can say that HB times LBE minus HPCD times LPCD will be equal to 0. From there, we can determine HPE to be equal to 160 ampere turn per meter. Using the BH curve, we can now determine B1, which will be 0.97 Tesla. We know the area of cross section and we know the value of B1. Thus, we can easily determine the value of phi 1, which will be equal to 5.82 into 10 to the power minus 4 Weber. Now, if we observe the data table, we can see that section EFAB, which is this portion, we don't know the value of phi, B, H and HL. We know that from the given information in the question, phi t equals phi 1 plus phi 2, which will be equal to 7.32 into 10 to the power minus 4 Weber. B equals phi t by A, which will be equal to 1.22 Tesla. From the curve of BH, we can determine H to be equal to 400 ampere turn for this section. Now, applying Ampere's circuital law, we can easily determine the value of I, which will be equal to 1.76 ampere. The remaining section has been done to demonstrate that mu is sensitive to the magnetizing force H. The permeability of each section is determined as follows. Problem 6. Calculate the magnetic flux phi for the magnetic circuit. In this case, I, N, area of cross section and length is given. We need to determine the magnetic flux phi. By Ampere's circuital law, we can easily determine the value of H, which will be equal to 1000 ampere turn per meter. Using the BH curve, we can determine the value of B to be equal to 0.39 Tesla. We know B, we know area of cross section, then we can easily determine phi, which is equal to 0.78 into 10 to the power minus 4 Webers. In the previous examples, from problem 1 to problem 5, we were asked to determine the current required to establish a specified amount of magnetic flux phi. In question 6, we were asked to determine phi for a given amount of current. In this case, which is problem 7, we are asked to determine the magnetic flux phi for the series magnetic circuit for the given MMF. The difference between problem 7 and problem 6 is that in problem 7, there is an air gap incorporated within the structure. So, the approach towards this problem will be slightly different from the previous ones. At first, we assume that the total impressed MMF is across the air gap. That is, the rise in MMF over here will eventually drop off through the air gap. Thus, Ni will be equals to HgLg. Using these values given in the question, we can determine H of G, which will be equal to 4 into 10 to the power 5 ampere turn per meter. Now, we can determine the field density, which is Pg, using this expression, which will be equal to 0.503 Tesla. We know that all the flux traveling through the cast iron will also travel through the air gap. Thus, phi g equals phi core, which is equals to Pg times A. Thus, phi core will be equal to 1.51 times 10 to the power minus 3 Weber. We know that the rising MMF, that is Ni, will be equal to the summation of all the MMF drops. Thus, using this value of phi, we will try to determine Ni and see whether our calculated Ni matches with the given product of Ni in the question. So if we fill out this table, using the BH curve, we can determine the value of H for the core. Then the drop of MMF across the core will be H core L core, which is equals to 240 ampere turn. Applying Ampere's circuital law results in Ni equals H core L core plus Hg Lg. So, the magnetic flux phi core, which we have calculated in the previous slide, using that value, if we try to determine Ni, then that value will be 640 ampere turn. Whereas, using the values given in the question, if we determine MMF rise, that will be 400 ampere turns. These two values are not equal. Why? Because we neglected the reluctance of all the magnetic paths but the air gap. The calculated value is greater than the specified value. We must therefore reduce this value by including the effect of these reluctances. Since approximately the difference is around 37.5% of our calculated value is above the desired value, we will reduce the calculated phi by 30% and see how close we come to the impressed MMF of 400 ampere turns. If we reduce the value of phi by 30%, it will be equal to 1.057 into 10 to the power minus 3 Webers. Again, we make a new table and fill in all the required values. We can calculate B using the expression phi by A. Now, B will be equal to 0.352 Tesla. Then we determine HgLg using this expression, which will be equal to 280.90 ampere turns. Using the BH curves, we can determine H core to be 850 ampere turns per meter. Then H core L core will be equal to 136 ampere turn. Now, if we apply Ampere's circuital law, Ni will be equal to 416.19 ampere turn. This value is within plus minus 5% and therefore acceptable. The solution is therefore phi equals 1.057 into 10 to the power minus 3 Webers.